Hi, students. I'm going to give you a short tutorial about your project. So we are going to see about the AC analysis of a BJT. So before going into the details of the AC analysis, just a quick review about the Bode plot. So Bode plot is basically a terminology which is expressed as 20 log of gain. Okay, so gain could be the ratio of output over input. For example, ratio of output voltage over input voltage. And it is usually plot like this one, that we have x-axis which will be in linear scale. For example, this is frequency, and you are plotting the gain of your circuit with respect to frequency. Okay, so this y-axis is in dB, and for example, let's have a look. Let's say the graph look like this one. Okay, so the gain of your circuit is varying according to frequency with this trend. Okay, so this is typically a graph of a high pass filter. Okay, so low pass filter graph will look like this one, high pass filter graph will look like this one, and if you combine them together, that high pass with the low pass, so the graph will look like this one. So this is basically the graph of a band pass filter. So when we analyze any circuit, so we will have the maximum value of gain. Okay, so that is basically sometimes called as K, or that will be the maximum value. For example, this could be the maximum value, this could be the maximum value, this could be the maximum value. Then we have some critical frequencies. For example, this is a 3 dB frequency. So this is usually calculated as 1 over 2 pi tau. Okay, so critical frequency is 1 over 2 pi tau. What is tau? We will see very soon. Okay, that what exactly is tau here. Okay, similarly for the low pass filter, that is the cutoff frequency. Okay, we usually call this as a F high. Okay, and this is usually called as F low. And if we combine them, that this is F high, this is F low, so this is basically the band pass filter, and the difference of this is called bandwidth, F high minus F low. So important thing is, if you want to calculate these frequencies, so it depends on this formula, 1 over 2 pi tau. So tau is basically the time constant, which is usually the product of R and C. Okay, R and C. That if in your circuit, if you have a capacitor, okay, for example, this is a series circuit. So if we have a capacitor, okay, then that capacitor multiply with the resistor. Okay, that this capacitance multiply with the resistance. This resistance is seen by this capacitor. Okay, resistance seen by this capacitor. What does this mean? For example, if we want to calculate that what is the resistance seen by this capacitance, so we will just make this open circuit, and any source, for example, voltage source or current source, they will be removed. So voltage source is always short circuited. Okay, we make open wherever we want to look, and the rest we will just draw our circuit. Okay, to Rs into Rp. Okay, and we want to see what is the resistance seen by this capacitor. So if you look at this from this point, so these two resistors are in series. So the resistance seen by this capacitor is basically Rs plus Rp. So the tau will become Rs plus Rp times this capacitance value, and frequency will become 1 over 2 pi of tau. So this is the way to calculate the frequency. This is a shortcut, the direct way, and if we calculate the transfer function, the gain of this circuit, okay, that we can calculate, okay, by drawing this expression. Like you can easily, like if you draw the AC circuit, so the capacitor's impedance will be 1 over SC or 1 over J omega C, okay. And if you write the expression using KVL, we can get this expression for the voltage, output voltage over input, or the gain of this circuit. And if we just do some rearrangement, which is not the focus here, So we can get basically the gain expression look like this one, that we have a constant which we can represent using k, and this is basically your tau which we just calculated. Okay, so s tau our 1 plus s tau. So if you put up the frequency value, for example s is equal to j omega for couple of points, so we can see that basically this expression can be plotted like this one, and this will be the maximum value, or the maximum value can be here the k, maximum gain value basically. Okay, so for this case we will get the maximum gain value when your frequency is very high. Okay, so if you put omega is equal to infinity, okay, s is basically j omega. So if you put omega is equal to infinity here, and if you simplify, so basically this will equal to k, the maximum gain value. So that is the gain of this circuit. Okay, so this is basically a high pass filter. So a series circuit like this will look like a high pass filter. Similarly, if we have a parallel circuit like this, so quickly, for example, we want to calculate the tau. So tau will be the resistance seen by this capacitor. So if I draw this, it will look like this one. Open circuit, RP. Then we have here RS. Okay, and this voltage circuit will be, source will be short circuited. So look at the resistance seen by this capacitor. So now RS and RP are in parallel. Okay, so here the resistance seen by this capacitor, it will be RS parallel with RP. So tau will be this resistance multiply with this capacitor value, and the frequency will be 1 over 2 pi of this tau. Okay, so for example, if you calculate the gain, okay, if you look here, this look like this one, k 1 over s times t. Okay, so this is basically your s here. Okay, which is the same as we have calculated here. Okay, RS parallel with RP. And if you plot this, it will look like this one. Okay, so this is basically the frequency. Okay, this is the frequency which we can calculate using this formula, 1 over 2 pi tau. Okay, low pass filter. And if we combine them, okay, like the series circuit and the parallel capacitance circuit, okay, so basically for these both circuits, so this series circuit provide us high pass characteristics, parallel circuit provide us low pass characteristics, and if we combine them, it will become basically a band pass filter. Okay, with the high frequency which is coming from basically your series circuit, and with the low frequency which is coming from your parallel circuit, and both can be calculated as 1 over 2 pi into tau for each case. Okay, as we did. The same strategy can be expanded to basically the BJTs. Like if you have a BJT circuit, like for example this common emitter, so you know very well, you have learned in the electronics 1 that we can make the AC model of this circuit, which will look like this one. Okay, so you can review the earlier lecture that how we can make this AC model. And in this AC model, basically the important parameters are basically the R pi, okay, and the beta, okay, which we can calculate from the DC analysis, which is not the scope here, and these values basically are provided, okay, in your project. Okay, so you can use this. So this circuit can be converted to this one. Now because we have capacitor and we are basically analyzing their frequency characteristics, so as I said earlier, the impedance of the capacitor is basically 1 over j omega c. So its performance is basically depending on frequency, and based on this performance, okay, frequency dependent characteristics, we can get different kind of filters. Okay, so now if we want to analyze that what kind of filter this circuit is representing, so the easiest way is that you get its transfer function, okay, the ratio of output over input, okay, and that we can get from the AC circuit, okay, like the AC model like this one. Okay, for example here you can write your output expression, and you can write the input expression. Okay, and from that we can get our desired. Okay, for example, if we just write the output expression here. Okay, so the output, like this current is flowing, so negative of this will be flowing here. So output is basically this current, which is basically negative of Gm times V pi times Rc. That is my output expression. Okay, and if I want to write the input expression, so input voltage is coming basically here. Okay, so what is the basically the input voltage here? We can easily write that. So to write the input voltage, what we can do here? Okay, first let's try to write that what is basically, let's define this parameter as Vx. Okay, and let's try to write this expression. Okay, so this Vx, okay, that will be basically the voltage drop here across this point. Okay, so the voltage drop across this point is basically the voltage drop across this complete branch, and this complete branch is basically what? Rb parallel with this resistance, which is basically what? R pi plus 1 plus beta. Okay, why 1 plus beta? Because this is a meter side times Re. Okay, I'm applying the KVL. So this resistance divided with total resistance of the circuit. Okay, so total resistance will be this one. Okay, plus the remaining circuit. So here we have R SC plus this capacitor 1 over SC, and this will be multiplied with our input. Okay, so this complete, it will be multiplied with our input. Okay, so this is the expression for the basically Vx, or in terms of that we can Vi. So if you take the ratio of V out over Vi, we can get our voltage gain. Okay, so by using those values we can actually get an idea of the filtering characteristics. Now for example, if you want to analyze, okay, let's have a look at this example now. Okay, for example, this is a circuit, a typical circuit, and let's try to find out the corner frequencies and the maximum gain. Okay, now we can draw the AC model, okay, which will look like this one for this circuit. Okay, and these values are given basically in your project. You have to find these values, okay, for your desired frequencies. Now by using these values we will find the frequencies, corner frequencies, okay, and the maximum gain. So to get the maximum gain, first thing is try to write the transfer function. Okay, the voltage ratio of output over input, which you can get from the AC analysis. For this circuit it will look like this one. Okay, and if you put up all the numbers and simplify this, the answer will be 2.47. There is a trick. If you want to get the maximum value, okay, what you can do, you can basically remove the capacitor. Okay, so if you have series capacitor in your circuit, they will be short circuited. Okay, and if you have parallel capacitors, they will be open circuit. Okay, so basically you can make them short circuit, and with the short circuit capacitors you can get the transfer function, and that will give you the maximum gain value. And even if you have your transfer function, just remove the capacitance effect. Okay, make the series capacitor short and parallel capacitor open, and in that case you will get the maximum gain value. Okay, now for example, let's try to analyze the corner frequencies. So there are two capacitors here, so we will have two corner frequencies. Okay, now for the first case, Okay, so the corner frequencies, for example, let's try to find out what is the corner frequency of this. So the rule is make the open circuit from that point. Okay, here we have RL, ground, and from this point here we have RC going to ground, so basically the same point, and then we have current source. Okay, so basically we have to remove all the sources. So this is a current source, so this will become open circuit. So basically when it is become open circuit, I don't need to go this side because the current is 0 now. Okay, so this circuit is basically removed. I have to put focus only on this. So the capacitance which is seen by this the resistance seen by this capacitor C2. So in this case, these two are in series. So this resistance basically will become RC plus RL. Okay. So tau for C2, it will become RC2 times C2. And frequency of C2, it will be 1 over 2 pi of this tau. So if you plug in the numbers, you can get this corner frequency. Now, if you want to look that what is the corner frequency for this one, okay, so again you have to draw the circuit for this one. So let's try to draw. So make the capacitor open circuit. Here we have RS. This voltage source, it will be short circuited. Then here we have RB. Okay, this is ground. And with RB we have R pi. And here we have RE. And this is a current source, it will be open. Okay, so we don't need to go here. So now if you look at this one, okay, this circuit, okay, so let's try to get the expression here. So the resistance seen by this capacitor, so that will be RS. Okay, that will be in series whatever resistance coming here. Okay, RS will be in series whatever resistance coming here. Let's define this as RIB. Okay, so RIB basically will be what? This RB that is parallel with this resistance. So that is basically R pi plus 1 plus beta times RE. Okay, so basically RC1 is RS plus this resistance. So tau for this one will be this RC1 times the value of this capacitor, and its corner frequency will be 1 over 2 pi times tau. Okay, so by using this basically we can calculate these corner frequencies. Now if you look here, this is RIB value. If you plug in the numbers, this is the tau for the C1, this is the tau for the C2. If you plug in the numbers, so this is the frequencies F1 and F2. So F1 is basically 70 Hertz and F2 is 2.4 Hertz. Okay, so if you plot them here, so this is like this one. This F1 is basically like 70 Hertz. This F2 is basically 2.4 Hertz. So the graph will look like this one. That this is the first corner frequency, this is the second corner frequency here for this case. This is another example. Okay, like we have more capacitor here, so that will be the AC model for this one. And now again quickly, for example, let's try to find the resistance seen by this capacitor. So for this case, our circuit will look like this one. Okay, so voltage source is short circuited. Now here see, we have a capacitor. Okay, so the parallel capacitor, okay, it will be basically, whenever we are considering this capacitor, we have to remove all the other capacitors. Okay, so we have to make them short circuit. Okay, so we are considering C1, so we will remove all other capacitors. Okay, so this CE capacitor, it will be short circuited, this will be short circuited, but again here, because this is the current source, this will be open circuit, so we don't need this circuit, this part. So if you put focus here, so RC1, okay, so this will be this RS plus the resistance seen from this point. Let's call this RIB. And this RIB will be what? This RB parallel with this branch. Okay, now see here, this is the short circuit CE, ground. So this in parallel with this one, basically this will become ground. Okay, so this will basically shorten this RE. So we have only R pi here. So RC1 will be this one, and its tau will be this RC1 times this capacitor value, and its corner frequency will be 1/2 pi this tau. Okay, and if you plug in the numbers, we will get this value. Let's look at this one, C2. So again, all other will be removed. This is open circuit, so we don't need to go this way. So this tau C2 will be this resistance, which is actually what? These two are in series now. So RC plus RL. So tau will be this resistance times this value, and corner frequency will be 1/2 pi tau C2. So again, if you plug in the numbers, we will get this answer. Last one, C3. Now we are focusing here, so we will remove the all other capacitors. So this is short circuit, this is short circuit. This will be open circuit. So means we don't need to go this way. So we have to put focus this side. So now if you look from this end, RS is in parallel with RB, right? RS is parallel with RB. Okay. And this combine is parallel with basically, and this combine, these two combine is in series with basically R pi. Okay. And what is next coming? Okay. And then it is basically becoming, okay, in series with this one. Okay. This is basically, these two are in parallel, and they are in parallel with this part, and then this is becoming in series with this one. So if I write this, it will look like this. Okay, that RS parallel with RB, then it is becoming in series with this R pi. Now because we are looking from the emitter side, and this is the base side, so this all resistance will be divided with 1 plus beta, and then they are in parallel with this RE, okay, from this end. So parallel with RE. So that is the resistance seen by this capacitor. So this tau will be this resistance multiplied with this capacitor value, plug in the numbers, we will get this one. Okay. And similarly, you can get the transfer function, the ratio of output over input, and you can get the maximum value. Maximum gain will be if you remove these capacitors. Okay. So this capacitor will be short circuit, and the other ways. Okay, so that is a further analysis. So I hope this tutorial will help you to do the manual calculations for the summation of your phase 1. Thank you very much.